Let's give one more theorem and proof. The theorem is very important. The proof is going to be slightly more intricate than the last few proofs we have seen. So let's say we've got a matrix A, and we've got n distinct eigenvalues. So there's no repetition in this list. And now, let's make a list of n eigenvectors corresponding to those eigenvalues. So for example, v sub 1 corresponds to lambda 1, v sub 2 corresponds to lambda 2, and so forth. In general, A times v sub I equals lambda I times v sub I. Then this set is linearly independent. Let's prove it. By way of contradiction, suppose not. So suppose this is a dependent set. Well, certainly the set containing only the first vector, v sub 1, this set is linearly independent because v sub 1 is an eigenvector. It's definitely not 0. This set might be linearly independent, or it might not. If it's linearly dependent, we stop. If it's linearly independent, we keep going. So what we're going to do is we're going to keep adding these vectors in order and one by one until independence breaks. So the first p vectors are independent. But this vector breaks independence so that the entire set is dependent. Now, if we have a dependent set and some vector in it is a linear combination of the previous vectors. And certainly that can't be the case for any of these vectors, because this set is independent. So it must be this last vector, the vector we added that broke independence and made this set dependent. So that last vector is a linear combination of the previous vectors. And what we're going to do now is multiply both sides of this equality by the matrix A. On the left, this multiplication will distribute over this addition and give us, well, for example, A C sub 1, V sub 1, but C sub 1 is a scalar, and we can move scalars around. So we'll move each of the scalars to the left. And now we're going to use the fact that these V's are eigenvectors and that A times V is the same as scalar multiplication. So this is C sub 1 times lambda 1 times V sub 1, and so on down the line. On the right-hand side as well. The next step is probably not very obvious. We're going to go back to this equation, and once again, we're going to multiply the left and the right-hand side by something. This time, though, it's going to be lambda sub p plus 1. Sorry, didn't. No, I did that right. So C sub 1 times lambda sub p plus 1 times V1 plus C2 lambda p plus 1 times V2 up to this. And on the right as well. And now we're going to subtract this from this. And we're going to get c sub 1 times lambda 1 minus lambda p plus 1 v1. We subtract this from this, and we pull out the common c1s, and we pull out the common v1s. And so on down the line. And on the right, you get 0. And now we're practically done. These first p vectors are independent. This linear combination equals 0. So these coefficients must be 0. Well, each of these coefficients is a product, c times a difference. But because our eigenvalues are distinct, there isn't any repetition in this list. This, for example, cannot be 0. And the zero product property says for multiplying two things together and they equal 0, one of them has to be 0, two real numbers. So c sub 1 is 0, and so on down the line. C sub 1 to C sub P are all 0. This is a contradiction. Why is it a contradiction? Because of this. If all of these C's are 0, then the entire left-hand side of the equality is 0. And v sub p plus 1 equals 0. But v sub p plus 1 is an eigenvector. 0 is the one thing it is absolutely not allowed to be. So the assumption we made that these are not linearly independent must have been false, and in fact they are linearly independent.